topology and some other stuff about some other tensor models that could be there in my application. So SYK, attractive tension, field tension as a possibly simple model of holography. And tensor models are these without-random couples that have similar dynamics to SYK model in the sense that in the larger limit the diagrams are dominated by melonic diagrams, although there are differences. Okay, and so this was the so I'll give a motivation even though people may be with all this. So SYK has a random coupling, but these tensor models have non-random. So there's three large n limits which we now know about that are very solvable. So vector models are good in the sense that they're diagrams can be explicitly summed. At some level, the dynamics is trivial and similar to field theories, and this manifests itself in that holographic tool of various vector models are going to be highest gauge things. So matrix models are in the sense that they have two indices and they give rise to a larger limit in which linear diagrams cannot be explicitly summed, but the advantage, what makes them interesting, that the dynamics are non-trivial, and these theories, we at least know some examples where the dual is an Einstein type theory of gravity, at least with supersymmetry. And then the new large n limit, which people are studying recently, are melonic tensor models, in which case fields with three or more indices can give rise to a large n limit, in which all leading diagrams can be explicitly summed in principle, but the dynamics is still, well, is more non-trivial than vector models. Okay, unfortunately, generally this large n limit, at least for higher dimensional conformal, higher dimensional field theories, doesn't always exist. So we'll see that if you just sum up these diagrams, you oftentimes get conformal field theories with complex scaling dimensions for the operators, for example, which basically means that, or that the fixed point has a complex value for a coupling constant, which in other words just means the fixed point doesn't exist. Okay, so although, okay, and yeah. Yeah, so I include bifundamental theories in matrix models as well as adjoints. Okay. In fact, yeah, we'll probably only consider, bifundamental. Okay, so just to review, we sort of have an understanding of the relation between vector and matrix models.
In other words, if the melonic model is if the indices are at the same time, then of course it would be very complicated.
You're saying ON with symmetric traceless representation of a single group, you're asking?
Just a single group, yeah.
Symmetric, say symmetric traceless representation. So I believe people have recently shown that they're also dominated by melonic. If you consider specifically ON symmetric traceless model, and for a while it was a conjecture that was supported by destroying diagrams. So that can also be studied, symmetric traceless, and may in fact be also melonic. Okay. Though there will be differences, so you could study the gauge, maybe small different numbers of people. Okay, So you can sort of think of how are the vector models and matrix models related, thanks to the existence of this theory called ABJ, which is UN cross UN Chern-Simons theory. So when M and N are both equal, it's ABJM theory, which is dual to Einstein gravity. So, a theory of Einstein gravity, namely type 2A supergravity on ADS4 cross CP3. But when M is sufficiently small, this is effectively a vector model, and only a small set of planar diagrams are dominant. You can, in principle, then solve the theory at strong coupling, or via indirect arguments show that the anomalous dimensions of higher spin. Well, the theory is a vector model. When M over N corrections are taken into account, more and more planar diagrams are included. At any given order of M over N, you could, in principle, sum all these diagrams. But if you were to try to sum them all, then it wouldn't be possible. And so when M over N is order 1, you have a matrix model. So there's sort of a theory which sort of, with a parameter that interpolates between the vector model and the matrix model. And from the point of view of the dual is that you have, okay, I mean you can argue that ABJ theory, as Shaz have done, has just a higher spin dual, and when M over N is 1, there's more operators. So the question is, we want, you could ask, is there a similar picture for tensor models, similar to the ABJ triality picture for matrix models? And I'll sort of argue there isn't a similar picture, but at least this is the relation between matrix models and vector models, and if we can, it would be nice if we can find a similar relation, a similar picture for tensor models, and how the melonic model relates to the other models. So, any questions on motivation? Okay. So what are the tensor models, just quickly again? So you can consider fields with three indices, which we take to be in different groups. It's best to take all the groups to be ON, but here I have UN groups, and you can draw a triple line notation for these fields, with each field in a different color. Each gauge group index with a different color, and then loops of a given color could correspond to factors of N, D, and M. Well, it had to be, you can't make them all 3U if you want the fermionic model, because you would have, if you want a tensor, well, if you want a tetrahedral interaction, because here B1 and B1 are contracted to psi bars. Okay, whereas where A1 and A and C indices, I can contract psi bar to psi and psi bar to psi, but the third index, one of the indices will have to go to the same tensor. So if you want a tetrahedral coupling to be allowed, then one of them has to be ON. You could have all 3 O, and there are reasons why that is actually better, but on each edge. Right. So you have to keep one of them without an arrows. Okay, and then this is sort of the diagram which dominates, and it's G squared N cubed. Okay, if you keep all the ranks equal. If
you, okay, so we use this to define a drift coupling, and then only melonic diagrams contribute in the large n limits. Okay, and these are what the melonic diagrams look like. You just draw the circle, like you just, yeah. So to the extent that they look like melons, that is the origin of the name melon. Okay, so here this is not SYK model. It has a non-random coupling, and it's studied by Klebanov and Tarnakovsky. And you can calculate its spectrum and 2-point function, and because the Schwinger-Dyson equations are identical to those of the SYK model at level of the spectrum of bilinear operators and the 2-point function of psi bar psi, it gives you identical results as SYK, but there are other operators which make it different. But okay, now the question we have is, can you generalize this to D dimensions? So one approach to generalizing to D dimensions is to consider a theory with a bosonic term, because a 5-4 interaction is relevant in less than 4 dimensions, and just formally solve the theory. Okay. Okay, when you do that, you find that there's generically a complex scaling dimension for the lowest mass bilinear. Okay, so even at level of a formal large n solution, which may or may not be approached as a IR limit, before you reach that level, you find generically there's a complex scaling dimension for a lowest mass bilinear. And the simplest explanation for complex scaling dimensions is that the conformal fixed point doesn't exist. If you were to still try to write down a holographic dual, a complex scaling dimension maps to a field with a mass below the F bound. So that indicates this. So you could think of it maybe as an unstable saddle point, or just that this fixed point doesn't exist. Okay, and instead what we did was something naive and sort of, okay, yeah.
So in the bosonic model, irrespective of what the sign of the coupling constant is, there are always
yeah, in fact, well, there's two. One is there's always unstable directions because this is not positive definite. It's like a weird thing, and it turns out there's always unstable directions. Is that, okay, you can still do a formal perturbation theory, like in phi cube theory, and it's still perturbatively renormalizable, but you get a complex fixed point or a complex scaling dimension. It didn't have to be, you could ask, is this complex scaling dimension related to that negative direction? And you'll see it's not, it's really just sort of an independent thing. It has, I don't think has anything to do with that negative direction. Okay, so the problem is different.
When you want to use the kind of melonic kind of variable, then and finding out the effective action of the epsilon, then you find that the saddle point is in the complex. I mean, it's a complex saddle point.
You find if you look for the spectrum of operators, you find, and you just look at real solutions to the eigenvalue equation, you'll find one is missing, but there's a complex solution which looks like that should be the dimension of the lowest mass bilinear.
So is it related to the solution of the gap equation means? In the bosonic version of the Gauss-Leber model, to begin with, what you find is the condensate is complex. But then you can inform the contour in the integration of this compensate
Right. So here there are only two ways we one way is you just solve for the spectrum of scaling dimensions by looking at eigenvalues of the integration kernel. Okay. Okay. So you look at you look at 3-point functions that so in the strong coupling limit the exact 3-point functions have to satisfy this equation. And there's the form of this 3-point function depends on the scaling dimension of O, and there appears to be a complex solution.
I think Gautam is asking the gap equation for the 2-point.
So at the 2-point function, you would not necessarily see there's a problem.
The propagator of the function.
The propagator looks fine.
I think that's your point.
You don't. Yes. So the scalar, the raw phi field seems fine. You might not have seen a problem at that level. So the idea is first let's just do similar calculations for a fermionic model in d dimensions. It doesn't have a negative direction, so you might hope that it's more promising. For that reason, the disadvantage is, of course, that when d is less than 2, it's infrared fixed point, but for larger d, the theory is not renormalizable. You might still think it could define a formal UV fixed point, say in d equals 3, just to the extent that one can define a formula.
Let me ask for the bosonic thing also. Just as an IR fixed point, wouldn't that be other operators in the same practical dimension that were also mixed? Just in the bosonic case. So you chose this particular tetrahedral structure.
Right.
Is that covered under a normalization group?
Okay, so if you do RG at finite n, you would also need pillow structures and vector-like structures.
Right.
Okay,
but
and
infinite n.
well, at infinite n, you also need them. I mean, n4 minus epsilon. So we can write down a beta function. Okay, in the large n limit for these guys.
So the final fixed point is not so simple. It has other structures.
That's right. Right. The final fixed point has a pillow structure and like a traditional vector.
And then once you have these other structures, does melonic dominance still happen?
Well, you can't find a fixed point. I mean, it would happen if you just draw diagrams. Okay, but if you now look for a fixed point in 4 minus epsilon dimensions, you find that that one of this other couplings has to be complex. Is that? But it's still melonic dominance from just diagrams, if you were asking that question. But the question, yeah.
That question, I just want to make sure I understand that. I mean, if I just wrote down vector-like interactions,
Right.
they would not be dominated by melonic diagrams.
Right.
So, but if you have an admixture of those kind of interactions, why is the whole thing still dominated by melonic diagrams? If the original UV Lagrange had an admixture.
Well, it's that those are like say you have a matrix model and a vector interaction. That vector interaction is just like a double trace deformation. So you can sort of ignore it or explicitly suffer.
I mean, depending on the power of n outside. You're saying that it can replace it by the expectation.
No, I mean we'll give it the usual scaling.
You're saying with Hubbard's prefactor. Phi ABC, the whole thing squared. You can write it as phi ABC times sigma plus sigma squared.
For instance.
And deal with that.
For instance, or if you don't do that, you'd still find. So I mean, the formal large n diagrams that would dominate will be just the melonic diagrams like this. But unfortunately, I mean, but if you actually, but those melonic diagrams do generate vector and things which would give a, you'll find that this double trace thing comes to a complex.
Let me ask another question that along these lines. Suppose I just took the fourth model in 2 dimensions with this interaction, or with this representation.
Right. So one of say any one of the gauge fields or all of them, you
all
add a
Curie QCD.
right.
All of them with this interaction constant.
Right.
Okay, so there's no interaction put in between the matter,
Yeah.
but integrating of the gauge goes on generates something.
Right.
In this theory, there would be no sense in it at all.
Right. Right. Because so integrating these out gives you a pillow-like interaction,
Okay.
which doesn't really give you melonic. Okay. So you have to add this other guy in, this other 5-4 interaction, or
once it's there,
then it's really in the large n limit. This is
The
what
dominant
dominates
Okay.
structure. You could find some non-traditional large n limit or something by scaling them differently, but in the natural scaling, those other guys.
okay, thank you.
Can I ask one
Yeah.
question? Even if the other vortices are there, I mean, don't we have to know how they scale again, the uplift, before we can decide whether they will destroy the melonic expansion or not?
Yes.
How do
Yes.
we know the end dependence?
I mean, okay. So let me skip. I might have drawn these in. Okay. So the other vertices might look like, for instance, a vector interaction like this, and or pillow interactions, which have 2 of them the same way and 1 a different way. So if you just look at corrections to the self energy, there's a natural scaling that comes. I mean, so for a vector model, I mean, you just, you have these sort of corrections. So you need to have, this is like G and this is N, so you, or in this case it'll be N cubed, so you need G vector times N cubed and fixed. If you just want the, so the way the other interactions depend on N, just there's a natural way it depends if you just look at the correction to the fermion self energy being finite in the limits.
Yeah, but I mean, ultimately you have to determine how they behave as a function of it at a fixed point, right?
Right. So so another thing you can do is you can just do a fixed point calculation and get without saying how they scale and then seeing other fixed points.
Okay.
Is that
Yeah.
what? And maybe there are other ways of scaling it hidden in there, but I mean when you do the large n. I mean, if you're going to sum all the diagrams, just maybe you can see how they would have to scale it before you find the fixed point. Usually,
Okay.
I mean in the naive.
So,
Okay. Yeah. Okay. Let me. Okay. So we can. Some of these points would come up. So anyway, we can sum the diagrams for all D the same way you can for a vector model, and of course the strong coupling limit is only the IR limit for D less than or equal to 2.
And once
So
again, you're assuming that the bare propagator is irrelevant when you do this.
right. So the bare propagator would be irrelevant for D less than 2. Okay, and for D greater than 2, in the UV, I guess, I mean, it's not irrelevant. So for D greater than 2, it would be only irrelevant in the UV, which means that probably lets, the D greater than 2 is not interesting, but
But if the gap equation you're summing is by throwing away the vector.
right. I mean, if you want a scaling solution, we throw in the
Yeah.
bare propagator, and And you can do that, and you'll get this strong coupling.
That is the scale.
That's the scaling.
Throwing away the moment.
That's and okay, and then you can now ask what are the spectrum of spin zero bilinears. Okay, this would be what the Schwinger-Dyson would look like schematically, and in strong coupling limit. Well, this should not be exact. This should be the free 3-point function. And in strong coupling limit, you throw away the first guy. So the strong coupling limit, the scaling solution, the sort of the 3-point functions are eigenvectors of the integration kernel, and you can write the diagrams and evaluate the integration kernel and plug it in for the allowed forms for 3-point functions, which depend on the scaling dimension, and then you ultimately get expression for this g, which you have to set equal to 1 by choosing appropriate value of tau. Okay, and then basic. Yeah. Say it's of bilinears.
I'm saying even in these theories, there would be the Wilson vectors which or not. I mean,
These are, I think, the Goldstone sector. I am not.
These are using the short scale. The analog. More related to excess and divergence, it goes to the exact IR.
Okay, the well, if there is a divergence, we get rid of it by dimensional regularization. Okay, but there's reasons why in higher dimensions you might not expect. Okay, because because those modes which are normalizable in one dimension may not be normalizable in higher dimensions. Is what.
But the argument that you drop that kinetic term, then the dual symmetry will become a local symmetry, and therefore.
But I guess a generic parameterization would stop you from being allowed to drop the. You can still only do those reparameterizations, which would be consistent with dropping the kinetic term.
Which is quite a lot, right? I mean, if you've got a Lagrangian with no kinetic term.
No, but well, I mean, if you were to do a diffeomorphism that made the kinetic term more dominant, what would have been the kinetic term?
No,
Well,
maybe.
okay, but okay, in some sense, it's true that those modes might be there. Okay, and we don't address that. Okay, so anyway, you can find the scaling dimensions, and okay, although spectrum is reasonable for d equals 3 in many respects, you do get a complex eigenvalue like you got in the scalar case. Okay. For d less than 2, however, there's no complex eigenvalue.
Just
Right.
I'll just get that. So if I wrote down your original UV Lagrangian but without the kinetic term, and then I just did a space-dependent rescaling of phi, and I choose phi to scale with the weight that compensates, that gets rid of the measure factor. At least at the naive level, that's a symmetry of the field.
It's symmetry of this strong coupling fixed point.
Of the strong coupling fixed.
But it wouldn't be allowed in the original.
In the original theory. That I agree. But I just want to see for the equations that you're solving, what is the symmetry?
That's true. That seems to be that.
So that would be now even larger than the xyk thing. Because that was reparameterized, that was function only of time, now it's of space and time.
Right.
And somehow that should show up as a zero mode, right? Because if you just look at the equation, you can sort of probably see by eye
Right, right,
Okay. Thanks.
right. At that. But I'm not sure these are normalizable zero modes in the sense of.
Yeah, and what is the issue? You mean if you compute the action for such a mode, whether it will be finite? That's the question.
Yeah.
Right, that's the issue. Okay.
Okay,
So, one could try to.
I mean, I think for the supersymmetric 2D model with random coupling, Witten claims they're not
They're not
normalizable.
normalized.
Yeah.
Okay.
But so this is the perspective that it's not necessarily just directly, yeah.
Yeah, I see. So like stiffness of these modes might turn out to be simple. That's interesting. That's very interesting. Okay.
He claims that happens for the random supersymmetric model in 2D.
That's very good.
But there are maybe other. I mean, if you have a global symmetry, you want global symmetry.
Yeah.
That's so maybe ON models are better than UN models for this perspective. But okay, there are some windows where you find the real spectrum, like near d equals 6 or 6 plus epsilon. Okay, so if you solve a spectrum, at least of scalar bilinears, for d less than 2, it's always real. The spectrum appears to be real. Okay, so let me. So these are the scaling dimensions of bilinears. Okay, of the form psi bar del slash. Okay, so so let me. Okay, so this is so there's this. So if say d is less than 2, you have this is the lowest. There's this eigenvalue here. Okay, if you increase d to be say a little bit larger than 2, this real solution isn't present. But you can argue it becomes complex. Okay, so you can't. So I guess you don't see the because this x-axis is real. You will not see them. But if you find a missing one, which then you check that there's a complex solution, you can find.
Statement about the scaling dimension of particular operator, or wherever you find one real solution, the rest of the dimensions there?
Well, I can find real solutions for any n except for 0. Okay, so the is that okay? So the idea is the bilinear operators are of a particular.
Sorry, what is the then?
Okay, so let me just find this. Okay, so say you have an operator which is of the form psi bar del slash with 2n psi. Okay, and it has scaling dimension which I'll just call tau. Okay. Then that's tau has to satisfy an eigenvalue equation of the form tau d equals 1. Okay, and so the blue here is g of tau d for different values d, and the orange line is just 1. Okay, and you expect tau to be 2 delta psi plus 2n plus something extra, which should go to 0 as n goes to infinity. Okay, so we find we find taus corresponding to each n except 0. We can do this for different d. So this is say d equals 3. Then this is for say d little less than 2 and d greater than 2.
Sure, I'm going to come back to this topic if you don't.
Yeah.
Now, let's say this rescaling, this conformal rescaling of psi.
Right.
If you take just the Lagrangian where you drop the kinetic that has to be normalized because it's just an exact zero. So
Right.
statements that of non-normalizability must be if you add in a bit of the kinetic term, then it becomes non-normalized.
Right, right.
Okay, but now I just want to understand the logic of this. In at least in higher than one dimensions, you've got a UV fixed point. The theory is
Yeah, so I don't think this applies to the d greater than 2 UV fixed point. So maybe we're not, are you asking about, say, the bosonic model in, are you claiming for the fermionic model in higher than d equals 2?
I was asking you for, I'll just say it.
Yeah.
You tell me. I mean, if you've got, I mean, in the traditional view of quantum field theory, so you see, what you're trying to do is define it in the situation where you're defining a UV fixed point. You're
Right.
defining a new fixed point.
Right.
Now, a fixed point is supposed to be well defined. It's the thing that defines the theory.
Right, right.
So, you know, you're not allowed to rescue the fixed point by looking at the perturbation. So if you've got these normalized, these large numbers of zero modes,
Right, so the way you know, we would define the fixed point strictly, okay, is okay, so here we find the dimensions and the epsilon. The way we would do it is you write down in action, say, the most general action, and you work in, say, 2 minus epsilon dimensions.
now this is the case where it is IR.
Well, say 2 minus epsilon dimensions, but you'll put a negative value of epsilon in at the end. Now, would that be,
That's the UV fixed point, right?
if you put, depending on what sign epsilon you
Right.
put in.
Yeah.
Okay. So, you know, if you were to get a real fixed point with a negative value epsilon,
Okay.
that seems maybe okay. I mean,
Maybe over. But I'll just say once again, I mean,
Right,
carry on
right.
talk about it later. But you see, the way that SYK rescued that theory was by saying that the conformal theory did not really make sense. Right? To give meaning to the theory, it was the slight breaking was important. Without that,
Right.
this thing did not really make sense. And quantum mechanics is weird, and they were dealing with an hierarchy. But our way of thinking, at least of UV fixed points.
right. So I agree with you that this isn't. I mean, the UV fixed point doesn't.
It's not completely, and it would not be a
Makes
solution
sense.
to the bootstrap equation.
You could check if it's I mean, of course, one can define it and see is there explicit contradiction to bootstrap.
But the thing that the purported UV fixed point has infinite. It's only by introducing the mass scale that you get something that's finite. And then you have to take that away somehow.
Right, right. So I agree with you that the UV
Okay, yeah.
fixed point isn't.
Okay, thank you.
But okay, so really, I mean, the idea, I mean, is you would study 2 minus epsilon with
Right.
epsilon positive.
Right.
I mean, formally, you get a solution in epsilon greater than 2, and you know, there are ways of you know, there are questions one can
Yeah,
ask,
maybe it's some way around it. Right?
but yeah, okay, and okay, so the idea is here, of course, we have solutions in the large n limit as a power series in epsilon, but you can hope to generalize them into finite n by just calculating a beta function in 2 minus epsilon dimensions, and each, you know, you'll find the fixed point is proportional, is depends on epsilon as usual, or epsilon fixed point. So you can try to determine a fixed point this way. So let me just start. Yeah. So the most general interaction for a three index guy will have these different terms. They look of qualitatively of 3 different types. There's tetrahedron interactions, which I drew here. Then there's pillow interactions in which 2 colors go sort of together and 1 color is different, and these are all the pillow interactions you can write down. Though you can reduce the coupling constants by imposing some symmetry, and then finally there's vector interactions where all the three guys go to the same guy. Okay, and so these are all the interactions you write down, and then one can calculate at one loop or two loop at finite n, either at finite n or at large n, keeping the natural scaling. See which interactions generate which interactions. Okay, so you find vector interactions only generate vector interactions in the large n scaling. Pillow interactions can generate vector interactions or pillow interactions. At finite n, they would also generate tetrahedron interactions, but not at large n in the natural scaling. And tetrahedron interactions generate all three. So if you start with a tetrahedron coupling, it would in general generate a pillow and vector thing, which you have to then include in the normalization.
And these are the only three types of only three gauge invariant for
or even bosonic for bosonic. It is just a statement about the colors, assuming only three indices, and four fields. Okay, and these are some of the terms that get generated, and you can calculate. So in the process of summing these, we would expect to get a beta function, but because the fixed point is sort of order square root epsilon for the tetrahedron, as we found, you have to go to two loops. So it's so the full beta function isn't finished, but when it is, then it allows you to study, for example, the tensor model in one dimension at finite n, or finite values of or nm and nm and d being different. Just like you can study the Wilson fixed point in 4 minus epsilon dimensions. So then presumably questions you might have, you might have questions about the theory at finite n can be addressed using in the series expansion at epsilon, which is a different way to approach bosonics.
Shiroman,
Yeah.
So if you want to do a big Hubbard step, which transformation in which you sort of define three kinds of fields. One is like just sigma, which corresponds to phi and phi, and then there's some sigma 8, in which you have two phi's, in which sorry. So some sigma and then some sigma 8 field and then some sigma 8 field, so something like that.
I don't think there's a Hubbard sandwich for the tensor, for the tetrahedron interaction. For vector model, it would be just like a uncolored thing for a vector interaction. Okay, you could, for pillow interaction, it would be like a gauge field. For one of, you can think of this blue line, for example, stretching it out. So integrating out a gauge field like a Chern-Simons field will give you rise to pillow interactions. Okay. But for tetrahedron, I don't know how to. I don't think anyone has come up with something to.
There is no way that you can write this theory in terms of some static one of some effective partial simplex.
Not that I'm aware of.
Yeah, the whole tetrahedral literature is completely. I mean, this is an obvious question. Yes. How does the large n limit work? Yes. Right, in terms of master field. Yeah. And it's just totally not addressed.
I mean, yeah, because you can't, at least you can't peel this apart simply.
Yeah, like you can't do it in the traditional way, but there must be some way of doing it, like some path integral manipulation. So let's revert Gautam's question.
Right.
Is there a Schwinger-Dyson type path integral manipulation that allows you to derive the gap equations?
You know what I mean?
Well, do these guys do like Stanford and Snelson do something?
I'm just ignorant of that. How does that work?
I don't remember how it works. But I don't think there is such a thing. Really.
I can see that, but for your pillow, it seems
Pillow you can do such a thing.
that there is a
So pillows to me themselves are not so interesting because, you know, I mean, it's really like, it's like a large N, but there's like, so if you think of this as a gauge field, it's like there would be N squared flavors for an order N gauge field. So it's just like a large flavor sort of. Okay, so you could peel this apart to have a line with two colors. And that might, well, you would have to somehow ensure the propagator twists them, like twist these blue lines. I don't think you can, like what will the kinetic, maybe it can be, you know, because of this crossing, it seems that it can't be, it's not that simple, yeah. Okay, so you could ask, there are various questions you could study for the 1D fermionic model and because I don't yet have the beta function, I'll ask the same some similar questions for the bosonic theory in 4 minus epsilon dimensions, because we have that because that beta function was calculated, I mean effectively was calculated by Mac and also.
Wait, sorry, just understand, the main motivation is to study the quantum mechanics, but at finite N?
Yeah.
I missed the motivation part.
Well, I mean, I just did a calculation, and that's the only sensible.
Okay.
That's like the sensible form. I mean, I did think, you know, maybe there's a melonic 3D guy, and I think we'll be able to. Yeah, but that's the main motivation, is you just develop epsilon expansion to study the one-dimensional theory. That's the only sensible motivation.
And epsilon is around it. Is
2 minus epsilon.
So you start at 2 and then try to go to 1.
Right, and everything, so that in the large N from the saddle points, it's completely consistent for that to work, and the spectrum is completely real for intermediate values. So it seems that it can be done.
If you go to this get 1 from 2 minus beta 1, then what happens to the extra kilo interactions and extra interactions?
No, so they will exist. They'll be there, and they'll have they'll be proportional to epsilon, or some powers of epsilon, and you have to take them into account when doing the perturbation theory.
For DZ one finite and these interactions will get generated. For DZ
Yeah, presumably they'll get generated from these pictures. So if you wanted to study the d equals 1 guy at finite n, you will get, these guys would get generated.
I see. You say that if you take a Wilson, I mean, of course, in quantum mechanics, you could just say this is my reply in the U.
Well, it's true that it's a 1D quantum model. I'm not sure do they get, but if you want to study it in 2 minus epsilon dimensions, these get generated, and there's a fixed point. You know.
Yeah, but I think the ignorant question is, how do you know that this 2 minus epsilon thing is taking you to what you called the tetrahedral quantum mechanics?
might take something else, which has some other thing.
Well, I mean, in the large N limit, this guy reduces to that.
Maybe even if in the UV you just specify the Lagrangian, what you're doing is not really specifying the, you're looking at the physics not really near the UV, near the fixed point.
That's right.
So it's near the IR. So there may be a sense in which those interactions are generated near the IR, even if your UV Lagrangian is whatever you specify.
Well, I mean, in perturbation theory, you get, if you start with a, you know, with some tetrahedrons at finite n, tetrahedrons, it gives you pillows in 2.
Right, but you know, a stupid question, but I could just declare, if I was really doing quantum mechanics, I could just declare once and for all, this is my Hamilton.
But say in the path integral formulation, you still have to be careful, even in.
So maybe if you do some sort of Wilsonian renormalization at some, and when you've got some effective scale cutoff, you've got some effect, integrating out things that happen.
Right.
But all the way at in the UV, you could just declare that my UV Lagrangian is the spectral.
With nothing else, yeah.
With nothing else. That could just be your declaration, and you could proceed from there.
Right.
But you said, I'm just trying to understand. Are you saying in your 4 minus epsilon, 2 minus epsilon expansion, what you're doing is generating the effective physics around the IR. Is this right?
Right. Right.
So it could, these things could be considered. Could be that the effective physics around the IR has other expansion, even though you will adapt into it. Is this correct?
Right. Okay, and so there are questions, because we have the 4 minus epsilon expansion for the 5-4. With tensors, there are questions you might want to ask there. So they look like this at finite n for 2 free orders epsilon, where you have a pillow, a tetrahedron, and a vector. Okay. And okay, so we can define a large n limit using the usual scaling. Okay, and then so the tetrahedral beta function just depends on G1, which is the tetrahedral coupling. The pillow beta function depends on the pillow and the tetrahedral couplings, and the double trace of vector definition depends on all of them. So this is with ON cross ON cross ON. So you could ask what would happen if you were to try to redo this calculation with ON cross OD cross OM. And okay, you can guess that actually in this case nothing changes, assuming you define, because you can define a different large n scaling. You can sort of absorb the m over n and d over n in the definitions of lambda of the 't Hooft couplings. Okay, so you still find a complex fixed point for any finite value of these ratios. Okay, and you can see that just because when defining the formal large n fixed point, you could have just defined it as, instead of n cubed g squared, you could have had g squared n md as lambda squared. Okay, so at the formal level, there's not an m over n expansion when these are finite. Okay, but okay, you could ask a simpler question. Say we were to do the bifundamental Wilson fixture fixed point, say ON cross OM Wilson fixture in 4 minus epsilon. So now we know that there's a well-defined fixed. Yeah.
So if I now put all the data functions to 0, so I get some particular values of the pillow and the tetrahedral
And
the couplings.
And you'll find
Complex.
one of them is complex. Like I think the vector is complex.
But I'm saying that
When epsilon is positive. Yeah.
is there a solution in which the pillow and the other thing switched off completely? I mean, what I'm saying is that can I recover from here?
No, so if you put, because beta pillow gets contributions from G1, I don't believe there's a fixed point with the pillow or double trace. You can set tetrahedron to be 0 from the beginning. You can't set pillow. If tetrahedron is non-zero, then these.
So the D equal to, I'm sort of asking two questions.
Yeah.
So the D equal to 1 is that it's the fixed point. How do I see from here? Or I just cannot.
Well, okay. This is the four. This beta function is for the bosonic theory, not the fermionic theory.
Oh, okay.
But you will get a similar beta function in the fermionic theory, and the claim is there the solution should be real when epsilon is positive. Okay.
Right. So I start from 2 minus epsilon and I do my
You'll get equations similar to this,
and I don't lambda.
but there should be a real solution.
Right.
The conjecture is there will be a real solution. Okay. Whereas if we do this for 5-4 with 4 minus epsilon, the claim is you get a complex solution. Is that And it's supported by the formal large N calculations, but one can actually calculate this and check.
And these non-zero other than the test variables, these other couplings contribute even in leading large N.
Well, they don't contribute in large N to the diagrams. I mean,
Why not? Because of the scalings of N. Oh.
well, I mean, the point these couplings get,
You're saying they're just generated by that.
they're generated by that. But if you wanted to calculate an answer in the large N limit, you could ignore those couplings, I think.
But suppose somebody just handed me a Lagrangian with these couplings where I want to say roughly the fixed point values. Just
Well, okay, they might enter in some trivial way, like double trace interactions can enter in a.
but they're not manifestly suppressed in large N. They're all in some naive way same order as large N. Is this right?
These are already the two like.
These are the Tuft-like couplings.
Yeah, just from the fact that there are no ends in your equation.
Yeah. So.
Yeah.
Well, the point is that I mean, yeah. So in principle, you have to include all these guys and draw them, and you can sum them. The contributions from pillow and double trace are sort of trivial.
Fine.
Okay, in the sense that you know, because they're like large favor or large, just a vector model in sum.
It's like in the
It's like a vector model. It's
the
trivial.
sigma field of the region,
Right.
It's like
Right. So you do need to keep all them, but these two are trivial as well.
Fine.
Okay, but you know this guy will have a real fixed point, but the other guys come out to be complex because of the way the numbers work. So anyway, we can redo this in a slightly simpler context, which was interesting to me for independent reasons. Was that okay? So 5-4 theory is defined for vector models, usually ON Wilson-Fisher fixed points in 3 dimensions. Say you were to generalize that to ON cross OM scalars with a similar, and look at the critical fixed point in 3D. So of course that's interesting because you couldn't talk of the M over N expansion, and we have the Vasiliev theory when M is 1, and so then what happens when you increase M over N, which is like the gravitational coupling. Okay, and because you can, in 4 minus epsilon, you can solve it at finite N, you can just try to answer this question. So it turns out when M equals 1, of course the theory is a well-defined fixed point in 3D. When M equals N, you also get the same phenomena here. You get a complex fixed point. Okay, and you can also again look. You can also do it for intermediate values of M over N, where alpha is M over N, and these are the beta function sort of equations. And it turns out here it gives you a real fixed point for M over N less than this value, and a complex fixed point otherwise.
How do you interpret this observation? Yeah, this is like the Wilson.
This is the Wilson fixer added with an extra OM symmetry, and now here there's two terms you can write down. There's this single trace term, which is like the matrix interaction, and there's the vector model interaction. Okay, and you look at the beta function for the two of them, and in the large N limit, how does it depend on alpha, which is M over N. Okay, and if M over N is less than this, I can find real solutions.
And this is just large N.
This is these are after scaling them to make the large N.
So just large N. Yeah, at the equal.
No. This is 4 minus epsilon.
4 minus epsilon.
Writing down, you do the finite N beta function.
Right. You can't do the large N at the equal 3 because
You can't solve it. Yeah. And now we scale the guys in the conventional scaling limit, so so this is what the beta function would be for as a function of alpha.
Good. But are you interpreting this as saying that there is no conformal field theory for M over N large enough?
I'm saying specifically this, if you're going to trust the epsilon expansion disorder, then there's no conformal fixed point for M over N bigger than this. Or I mean, of course, this is inverse symmetric. But
I understand.
Yeah.
But so this you want to take seriously, that this fixed point.
I mean, you can calculate corrections to this number in epsilon expansion. Well, here I didn't plug in any value for epsilon. I just asked, is the fixed point real, the leading order fixed point in epsilon expansion or not? And it's complex if m over n is so I don't know how to. I mean, the conventional interpretation would be that the fixed point doesn't exist. Okay, because how do you know a phi 4 fixed point exists for finite n? Because you can study it by epsilon expansion. If you take it that way. So, but what would happen? I mean, if you just put that interaction and see if you flow to the IR or something.
Yeah, but let me ask this. So I'm sorry, but if we just took this at d equals 3 around large, now you could, as long as both these operators, or the matrix of operators in this space has dimension greater than 3.
It's a IR. There's a IR limit you can imagine taking.
Right. You would think you're safe because you would suppose I start taking.
That's right. You would think you're safe. I mean, before I did this calculation, it was my conjecture of what would be the. Okay, and you can do m over n expansion as well.
Yeah, you can do m over n
But
expansion.
of course, this is a finite value of m over n. Where
I understand. But in the m over n expansion, it seems more or less guaranteed you won't see clusters.
yeah, and that's consistent. So here, so with this there being like a finite value, I believe this finite value would get smaller if you added a third index.
So could it be that what happens is that one of the operators becomes dimension 3 at this point? When m over n is 1, it is infinite. Well, m is the small operator.
Yeah. Well, when it's
0. M over n is 0. We know that these operators both have dimension 4.
right.
Okay. Now m over n interactions change their anomalous dimensions. Could start bringing them down. It could be that there's a point where one of these operators has dimension 3. At that point, all hell breaks loose. Maybe that's what's going on.
That's one possibility for what's going on.
Then there's a new relevant operator.
Even 4 minus dimension will be less than 4 minus.
So I was working at d equals 3. I was thinking of the d equals 3. When they're d equals 3, because these operators are dimension 4, they're irrelevant and they can't do too much exist. So for instance, as he was saying, in the m over n expansion, they guarantee to be equal. It could be that one of them becomes dimension 3 at some point, and then.
Well, I don't know if you would see that in 4 minus epsilon. Like here, it's just that you get a complex solution.
I understand. But I just want to understand what the interpretation would be from the point of view of a 3-dimensional.
So we're going 4 minus epsilon on the dimension. Right. Because even 4 minus epsilon dimension in the m over n, as you vary m over n, some operators come down to become relevant.
Yeah.
At that point.
Yeah, that's true. This is maybe more calculable in 4 minus epsilon. Because you see, in 4 minus epsilon, these things continue to be irrelevant, but only a little irrelevant. Where the irrelevance is controlled by epsilon.
So that might
Might be
be a way
computable
to
see.
understand
Yeah.
exactly what
It could be
happening.
that, exactly. Maybe you could actually see that this is what's going on.
Also, m equals 1 is a vector thing, right?
M equals 1 is a vector.
So what if m is equal to 1 and n equals 5?
Then that's a you can study them for here. I'm assuming m and n are large in this equation, but you have an equation
No,
where.
because then it's 0.2 which is greater than that, but there is still a vector.
Well, this is m and n both large.
Yeah, n equals 1 and n large.
But for n, it could be that there isn't a fixed point in that case. I mean, I can still look at the beta function finite n and n. And generically, there's not. I think if say if m is 2 or 2 and 5, then there isn't one.
Yeah, no, what I said was wrong. No, but Abhijit is saying that. Oh, right. Where is lambda? Where is lambda entering this?
No, so G1 and G2 are really lambda here. So these are both the.
What happens when lambda equals 0?
No, you can't. You have to find the fixed point. The alpha is m over n. And you have G1 and G2 as the two couplets. Okay, which correspond to a double trace and single trace
Yeah.
interaction.
No, I mean, yeah, so lambda is 0, we can still study this model of just scalar fields, right? This is really Wilson Fisher.
Right, right. So you can, there also is fixed point there, so that would be G1 being 0.
What? G1? Being 0.
G1 being 0. And then I think there's a fixed point.
But this problem that you mentioned didn't have lambda.
Well, I'm assuming a fixed point where G1 is non-zero. Okay, there may be also a fixed point where G1 is 0. So the fixed point where G1 is non-zero has a real value for G2 if m over n is in this range. Is that?
Wait, this is not the deformation of, if I took lambda to 0, this doesn't go just to the,
No, there's two fixed points. You have a beta function resolving to be 0,
Yes.
and there's just a few fixed points.
so what about the fixed point that follows the one that existed even at lambda equals 0? Let's take that
No,
and
so
deform it to finite lambda.
You can't deform that to, I mean, you know, either I set G, this have like discrete roots. So one root is G1 equals 0.
You say physics is discontinuously different. Lambda is very, very small.
Well, lambda is a coupling constant, right? You can't just tune it.
N and k. I mean, k is very, very
No, there's no k. This is just a 5-4 theory.
I could
Yeah. You can ask, say you were to add a Chern-Simons gauge field, how would this change?
I'm sorry, so
I don't know how
what
to.
What was lambda? I got those
Okay,
totally disordered.
So we're looking at 5-4 theory,
Yes.
but now the fields have 2 indices instead of 1.
Okay. And when
Okay.
you've got two indices, so it's only two couplings are G1 and G2.
Yeah, so then there's only 2 couplings you can write down. One is a single trace 5-4 interaction, which is like phi transpose trace. Or you can do a double trace guy. This would be the vector model interaction.
Okay. So you say n equals 2 is very different from n equals 1. Is that what you're saying? When n is 1, then it's really a vector theory, right?
Well, no, now I'm going to study this in the limit where n is, well, we have of course, the beta function for finite n and m, but because it's complicated, it's simpler to write it in the case when n and m are both large, but alpha is head
from what
fixed.
you've actually studied to just
Yeah.
what you think might be.
Right.
Okay, so we've got m and n, and if m is 1, then this is genuinely a vector theory.
But I think there the G1 is 0. That's
In there, G1 is 0.
So
the
you're,
person saying is that no.
yeah, so you're saying that if m is 2, that's very different from m is equal to 1.
Right, that's completely different when m is equal to
Even
1.
if n is a million. M is 2 and
No, if
Okay,
m
but
is a
then-
million, I mean,
so
this is
new-
fine.
Yeah, it's fine, but is that new fixed points in some sense near to the
Yeah,
vector
yeah,
fixed point?
that will be near to it.
I see. So it's like a deformation of that fixed point.
It's like a deformation, but there's always another fixed point where you just kept the matrix guy 0.
We both system
So there's
are the
2.
same.
Ah,
If n equals 1, then both systems are the same.
Yeah, that's what I'm saying. Then there's just one term.
that's why there's no possible issue.
So there's no issue. So your conclusion should also change correspondingly.
No, so here I'm presenting this when m and n are both large.
Exactly.
Okay, if there are 1 over n corrections to these equations.
So we could, do a finite.
Yeah.
Finite and right?
Yeah, you can. I believe, for m equals 2 and n, I mean, if you increase both m and n, then there's a
Yeah.
problem even at finite n. But
Okay, I understand.
What happened to what you are saying is if you do analysis, then these things generate into the event operator and you are saying that this analysis is not reliable. Are you saying that this analysis is not reliable and you cannot conclude anything from it?
What?
Suppose you are doing from C plus experiment.
No. Let's do d equals 3 and do an m over n. In that, I believe you will never have any.
yeah, because this,
Because
you'll never
this is
have,
highly irrelevant.
and you can just see the diagram. But of course, this is saying that for a finite value of m over n.
Yeah.
If you have both minus epsilon expansion with finite value
that might go away because there's a new operator you have to consider, and that runs up to infinity or something like that, at some finite m. Does Shiroman, do you think that's reasonable?
Well, I don't know what happens in that case. So
Yeah,
this
I
is a
know.
confuse, but that's one possibility. And it would be nice to know what happened, because that's like what happens in a particular facility of theory,
Yeah,
which is
sounds
well
like-
known.
It sounds like
And you can
there
ask
will
the
be a
Tuft
phase transition.
Tuft coupling and
Yeah.
Shiroman, maybe I will
Yeah.
do something. But suppose that I have a G1 plane.
right.
And on the G1 equal to 0 axis, I mean something in which you just have a whole Wilson-Fisher thing. Then there is
There's always a fixed point.
Fixed point is at some finite value of D2.
Right.
So it is some D2 star.
Right. Right.
And now I think of the entire G1 plane.
Right.
There are some isolated.
Well, there's another fixed point which when m over n is small would be very close to that.
So if alpha is okay, so if m and n were all large or finite, so what's the structure of these in a bunch of Wilson-Fisher fixed points in the G1 plane? They're parameterized by alpha, of course. Getting that?
Right. Right. So if
So there are some isolated fixed points in the G1 plane, and then there's some. So what? Yeah.
well, like if you look, there'll be two solutions to this equation being zero.
Two solutions, and they're parameterized by alpha, and
And corresponding, there could be. I mean, I guess
so there's an alpha.
to here there'll be also two solutions. So there are two fixed points. One is basically G1 is 0. One is G1 non-zero. When alpha is small, they're very close to each other. When alpha is big, they might go away from each other, and then if alpha is too big, the second one becomes complex. Is that I mean, the idea was that if you were to do this with positive epsilon in the 2 plus epsilon for the fermionic theory, you'd have a similar phenomena for the gross liver model. But it's not as rigorous because that's usually explored. So maybe it's better to do 4 minus epsilon in gross liver Yukawa.
Like the fixed point where one of the two G's is 0. That exists already.
Where the double trace sky is 0, you can always set the double trace sky to be 0.
Yeah, you can always.
Because that doesn't come in here.
And about that fixed point is the trace operator. What's the dimension of the trace operator?
Then it's I think in the larger limit it's just like it doesn't change.
It's 1.
Yeah, I mean it's the free dimension.
It's 1 rather than 2. But in the second fixed point, the dimension of the trace operator would be 2 in the larger limit. In 3 dimensions.
I don't know what it would be in that in 3 dimensions.
Well, I think you could figure it. I mean,
You can figure it out from in epsilon expansion.
no, just in larger limit. I'm asking a naive question. You know, I mean, when we say Wilson-Fisher, it's like some 5 to 4 coupling is becoming large.
Right.
Like the 2 5 to 4 couplings.
Right.
So I'm asking if they're both becoming large, then presumably in the larger limit D equals 3, every bilinear operator of phi is at dimension 2. But if only one of them becomes large, you might imagine that one of them has dimension 2 and the other one has dimension 2. And that sounds like your G1 equals 0 and G2.
No, I mean, and G1 and G2 are not on equal footing.
Okay.
Right. One is this guy,
Uh,
and the other is a double trace operator.
I understand.
Right. And the first guy generates itself only.
Okay, I
I mean, sorry, so G1 maybe I was confusing, but yeah, the point is the first guy, the second guy doesn't generate the first guy.
Right. Right. So I suppose my question is, in both fixed points in the larger matrix, do all bilinears of phi get very large anomalous dimension? Or is it true that some of the bilinears of phi get not very large anomalous dimension in one of them?
So I know in D equals 3 you can say the vector model large n limits, which is that G1 is this guy 0, and then nothing gets anomalous dimensions aside from phi itself, which is like replaced by
Phi squared.
no, phi squared would not, yeah, phi squared becomes,
But now there are many phi squares. So I'm wondering if
well, there's like, I mean, but it's a matrix model, so I have no idea what happens in the large n. I mean, I mean, if you have the double trace, then you can't solve it.
Right, in terms of another phi square. There seems to be, only for the double tracing, there seems to be managing sigma t. But the other coupling,
I mean, the other coupling now, it's just the usual matrix model, like, would your argument work for super Young Mills?
let me clarify. Suppose I take n to infinity and keep n equals 2.
Okay, okay,
Okay, now I've got a 2 cross 2 matrix of singlets.
right.
Okay, now I want to know whether this whole 2 cross 2 matrix of singlet fields becomes heavy or not. Okay,
Right.
now I suppose you're saying because flavor symmetry that must be true. Or what about the trace? The trace is different from.
No, then there's two couplings, and
Yes.
you can play, you
take the
can
traceless part
change
of that
them
2 cross
around,
2.
yeah,
Yeah, we can take that 2 cross 2, it's got a traceless part and a trace part.
right,
And these could in principle have different anomalous dimensions.
right,
And it could be that one of these fixed points, one of these two operators has anomalous dimension 0 and the other one has anomalous dimension 1.
right,
In a generic fixed point, you'd expect both of them to have the anomalous dimension 1.
right.
Now this is of interest to me because it's only the second fixed point that could be due to fermions. Right, because fermions will always have dimension 1. Dimension 2. Any
Right,
bilinear.
right.
And if there was another fixed point without this, it's sort of interesting how it would make both fermions.
Right. I mean, of course, if this theory doesn't exist, also, I mean,
Why not? We could gauge it, right? We could gauge the n. We could take OM times OM.
yeah, I mean, for particularly,
We could take OM times OM, keep n fixed, n gauged, then it's a very small deformation of the
Right,
theory we
right,
studied in
right.
detail.
right,
Everything we say would go through. There would be these two couplings, there would be these two different kinds of operators. Some of them could have anomalous large. It sounds amazing.
right. This is,
And there's the additional interest of both from duality.
right. So I think there'll be various consistency checks you can propose from duality.
Even formulating what the statement is.
Yeah, and formulating it and making it consistent is not trivial. Even for a bifundamental post-Fermi duality,
N
because this
equals
one
2.
doesn't.
Right, just forget bifundamental.
Okay.
Just
M equals 2.
M equals 2 as flavor symmetry.
Right.
Okay, so now we've got a bosonic theory with a U2 flavor symmetry.
Right.
That should be given to a fermionic theory with a U2 flavor symmetry. It had better be that at leading order, every bilinear for bosons has dimension 2. Because certainly anything is below the fermion polarity.
So it'll tell you which critical definition.
Which one is the right one. And then it could be, you see the ones that have dimension 1 are like critical fermionic theory.
Right.
So it could be an interesting renormalization group flow between these fixed points,
Right.
which has an interesting fermionic view. That sounds interesting.
Right. So if you want, I can more or less end with this. I mean, there are some other theories, but maybe this is not quite complete.
It's totally up to you. We have 10 minutes.
Okay, so, but anyway, so these are the questions that you could also formulate them in the fermionic case. I expect it would be real. I mean, and see. Maybe I'll just end it with this because there's this. Well, I'll just mention. So if you were to look at the supersymmetric theory, it also has a phi 6 coupling, the supersymmetric melonic tensor model. So you can this is not set, this is sextic. You can consider a bosonic theory with the following action. Okay, so here chi is an auxiliary field, but it's like a 6. Well, it defines a slightly new melonic limit. Sextic. It's supposed to be sextic. This autocorrect was bad. Septic just means it just autocorrected it by mistake.
Maybe it's a Freudian slip.
No, I mean, yeah. Yeah, so this, I mean, is 6 guys, but you can think of it as, you can think of it as a 5-6 coupling, or you can think of it as 2 fields, okay, with this auxiliary field. Okay, and if you write it in this auxiliary field, it's also melonic dominated. Okay, and there's two guys here. Two 2-point functions, and okay, there's some subtleties in its solution, but okay, so even if you just consider this model, you can ask what is the gap equation. Okay, so you can draw two melonic gap equations, one for F, one for this chi field, and one for the phi field. Okay, and they're coupled to each other. And okay, then okay, you can ask then for what allowed values of dimensions of the scalar field would it be consistent to drop the kinetic term? And there's a okay, the scalar field has to have these dimensions ranging from these two values. So basically for d less than 3, there's a range. If you actually solve, okay, so the point is this is another tensor model, which I'm investigating, and it may or may not have a real spectrum. So, but perhaps we just it's a convenient just end before. Okay. Yeah. Yeah, are there any other questions?
ICTS? HRI? Ashok has a class at some 12:30. He needs to come.
Oh, it's every day it's like that?
Every Monday.
Every Monday it's like that?
He said so. His class ends this week, so there was like
So, just to go back
Yeah.
to the question of the whole term. So, if I have this fermionic theory in T minus epsilon, is it that the IR scale that I'm landing at is different from the tetrahedral theory as it is equal to 1? And so, okay, so 2 questions. So this IR theory which I land at, starting from T minus epsilon and doing blah, is different from what would be the fixed point of the d equal to 1 theory. And the d equal to 1 tetrahedral theory has this goal. And your theory on the other hand does not have.
But I mean, I don't know if it has.
So what's the story of the?
I mean, at the level of the scaling dimensions of bilinear operators, there you get the same scaling dimensions. I believe that the modes are there. I mean, maybe you can't see them in.
And you know this thing that you have drawn here, the
even in 1D, if you just do it naively with dimensional regularization, you can solve for a spectrum of operators.
And you don't get that zero mode or whatever.
That doesn't,
Sure.
just even in just you write the 1D thing like this and you do the calculation. I mean, at various stages you might use dimensional regularization implicitly.
So it's just solving for the eigenvalues of the scale. You don't see that a problem. You just see this phenomenon that there is one of the eigenvalues
Is
that
2.
Is 2. Yeah. Do you see something like that?
Well, you do see an you know what the eigenvalues are. So there'll be one which approaches to 2.
There's one that approaches 2, but it's some.
Now you can try to look at higher spin spectrum and see is there a graviton. I mean, is there a spin 2 stress tensor or something? But
So the limits of this Schwarzschild would be which if you go to 1 plus epsilon, is that
so there's a question of what happens to this. Does it capture those physics or not? I mean, you can write down a CFT and the claim is you can do 2 minus epsilon dimensions, just following Roth procedure. Does that capture any of these subtleties associated with the fact the 1D theory is not quite conformal or not? I'm not sure. What to do that.
Let me ask you one more question. Suppose these higher dimensional theories, there are 2 points of view you may take. One is that this is a way of computing the 1-dimensional theory. Second, that you want to study the higher dimensional theories in their own right. We had a long discussion about the possibility of them being UV fixed points. Now I want to look at the possibility of them being IR fixed.
In 2 plus epsilon.
Whichever.
Well, you want 2 minus epsilon, just
Yeah. I want to see if just as IR fixed points they are just what
in fractional dimension.
in fractional dimension.
Right.
So
Right.
just what the structure is. So given, I mean, in the straight IR, you will see divergence. If you just drop the kinetic term, you see some divergence. Because that's this exact zero mode of the problem. Yes, is that right?
I don't know, where do you see the divergence?
Where would you see the divergence? Well, in the path integral way, if you try to do it at 1 higher order and 1 by n, you would integrate over these space of solutions, and that would be answer.
Okay.
Right. So that will have to be cured by taking a bit of this operator. So I'm wondering what that means. Normally we talk in terms of.
But could it be these are not normalizable unless
Yeah,
you're in
this is
one
what I
dimension?
this is what I want to understand. So let's say that the answer is that it's not wrong. I want to understand what is the final. What is the answer for the final IR dynamics? If you took this as the answer for the final IR dynamics, it seems to me that that's not well defined because you get a divergence. Is this right or not?
Yeah.
And then if you're saying it's cured, that seems to put a length scale into it. So I want to know if I go all the way down to the IR, what is this? You understand the question? And you saying Witten had something similar. What was his answer?
You're saying it does not. I mean,
presumably the statement about not being normalizable is a statement when you add the kinetic term.
right.
Okay, but adding the kinetic term adds a length scale. So I suppose my question is, what is the final answer? If the final answer is going to be generated by dropping the kinetic term, then that appears to have a value.
No, so I guess the final answer would be you take this particular solution, and this sort of spontaneously breaks.
Okay, and now I do one loop around this, in 1 by n.
And that'll be okay.
How will it be okay?
Because those will be non-normalizable, the problematic terms.
It's non-normalizable once you include the kinetic term. You're saying so you include even a little bit of it in that.
Well, 1 by n, would you have to?
Naively you get an action which has an exact zero mode at leading orbital large n, and then
I didn't completely understand his discussion. It was not
This is which
in the
paper?
2D, more on 2D,
More on
more and
I'll read
superset.
it. Okay, thank you.
And yeah, I mean even
But Shiraz, equal to 1
Yeah,
in the tetrahedral model.
yeah.
You found the worst case, right?
For the global symmetry.
So the global
Yeah.
symmetry and as well as the other influence sources. But for example, just the reparameter are just there. Now something different is happening here. He's becoming, I mean, so you're saying that these guys are becoming, so Shiroman, you're saying that these guys are becoming non-normalizing modes as well as they are not part of the partial right? But parameters get what?
only the subgroup that preserve this form, which would be just the conformal group. But even just from the spatial integral, would they be non-normalizable? We're saying, right? That couldn't be the case.
But I thought that without adding the kinetic term, they were exact zero. Maybe I'm wrong about that. But do you agree with that statement? That there is a moduli space of solutions to that equation without adding the kinetic. Is that correct?
Right.
That is an exact statement, right?
In the sense, we should just be able to.
Take a solution, map by some transformation, get a result. Just of the equation.
Right. Right.
I think that must be true.
Right.
Okay. So then we now start doing fluctuations. There's an exact manifold of zero mode, which should give you an infinity unless a pure.
But to calculate the action, you'd still need the kinetic term, right?
You need the kinetic. Now that's the issue. Right. So if you put in the kinetic term, you're saying it removes it. I think, yeah. So what you're saying is that you define clearly the epsilon kinetic term, and the limit epsilon goes to 0.
But that epsilon, you can do some scaling in your effective action, so that that epsilon is actually 1 over square root of j. Meaning that you can do some scaling in your sigma passing integral, so that or what Malcolm and stands for the g passing integral.
Right.
And then so although you have some j equal 4 or whatever, you can do some scaling of the passing integral derivative, so that guy, what would have been the kinetic term, it just picks up some 1 over square root of j or some such thing. And basically, turning on 1 over g, turning on 1 over j, finite 1 over j but small, it's the same thing as bringing back the kinetic term. And as a result, you get this contribution from the previous zero mode.
Right.
Finite 1 over j.
But in the limit in quantum mechanics, if you try to then take the limit j goes to infinity,
Yeah.
you get a divergence.
Yeah.
Right? So I think that what he wants to say is that it's
No,
different.
I'm saying that what you keep in that case the things that survive are just the conformal transformations, more or less. Not reparameterization.
Yeah, but right. So suppose you take the original theory. Let's just review what happened one day. You turn on the initial coupling, let parameterize x 1 over j or whatever. Then you take the limit j. And you get a finite answer. If you try to take the limit j goes to infinity in that answer, you get infinity. So that limit is not okay in that case. Now there's a possibility here that when you go above 1 dimensions, you turn on a deformation and then calculate everything and then take the limit to 0. And that limit is weighted. And that gives you the conformity. This, I think, is the sense of what you're saying.
Yeah.
Because what he's saying is that turning on any of this thing removes the problem. Just completely removes
Yeah.
it. You just infinity. I mean,
It it removes the reparameterization. You still have conformal stuff or whatever. Now, if you have a marginal operator U1 global simply, that can cause a problem.
But maybe that is also not normalized.
I think those might be known. So there's still those problems can rise, but it's if you didn't have that, if you didn't have those, then you might be able to get rid of it. Yeah.
So you say that it could be that this limit is well defined and that defines the conformity theory. And that might be true also for the UV theory. Perhaps that's true.
Well, the UV theory is still just, I mean, formal. It's not, I mean, but so that might, I mean, ideally you would want another way of defining the UV theory as an IR theory.
That may be, but just I just want to understand about the an unambiguous answer that makes sense, and then we can test whether it's
Is it that because you are generating many interactions, now you don't have this Shiroman, so now even if you take the limit to kinetic term stopping drop, you are not getting it.
I mean, I think what you say is that if they turn on kinetic term a little bit, that means infinite stiffness to the heat, no matter how small the kinetic term is. And if that's the case, then taking a kinetic term infinite element is very different from taking zero. Right? I mean, it's like the infinity value will come from the IR,
Come from the UV.
from the UV,
Well, you don't want the
jaggedy variation.
UV to, I mean, you can't have any variation that would stop, like any change that would make the sky subdominant.
But the non-normalizable part comes from very short distance and very long distance. Fact that's non-normalizable in this calculation comes from a divergence at short distance or long distance.
I think at short distance.
Yeah, so it's like a lattice regulation would make it. There would be some order of commutation of limits anyway. But your epsilon and your lattice regulation. I think that's what you're saying. It's very interesting. It's never occurred to me. Okay, thank you. Maybe that also is your way of defining the theory. I mean, whether it's valid or not, that's another issue. Shouldn't we be able to think of it as this thing generating some effective derivative interaction? Should we be able to find a fixed point containing a maybe conformal derivative interaction? Whatever that is.
Maybe you can. You mean like higher derivative actions?
Higher derivative or derivative with the metric. Like del phi by the appropriate power. Some strange moduli to the system. Because
Maybe that's
the
question.
strange thing about these theories from my point of view is they look like they're defined without a derivative. It sounds really strange. But there must, if they do make sense, there must be in the end some derivative.
Of course, I mean, to make all the argument of non-normal, you might have to also solve this numerically, with too
Fine.
strong, and
Fine.
then you can, yeah.
Fine. Okay, thank you.